Hello everyone guys. First of all, good morning to all of you. Now this is the mathematics tutorial, and so in this tutorial we are discussing about matrices, determinants, and such topics of linear algebra. So till this tutorial, till this session, we have just discussed, we have just know about what are the symmetric matrices and skew symmetric matrices, and also we have talked about the transpose of a matrix, and we also have looked at how to find the transpose of a matrix. So now in this tutorial we will look on some properties of transpose and symmetric and skew symmetric matrices, and also we will talk about determinant. So what is a determinant and how it formed and how it will be expanded, so we will know everything. So first of all, if you are a newcomer on this website, if you are a newbie, then please subscribe our channel and share its link. Okay. So now let's start the topic. This point says that every square matrix A can be uniquely expressed as the sum of a symmetric matrix P and a skew symmetric matrix Q, where P will be this and Q will be this. So actually this says that there is a square matrix A. So we can just express this square matrix A in the form of a symmetric matrix and a skew symmetric matrix. So what about this? Actually, P is a symmetric matrix. So we have to write a symmetric matrix. Then we should use two matrices. The first one is the A matrix itself, and second is the transpose of this A. So how to express this matrix in a form of symmetric matrix? So a symmetric matrix will be form of the half of a matrix and the sum of its transpose. So just A is the matrix itself and AT is the transpose of A. So the sum of A plus AT and then it's a half. This will be known as the symmetric matrix P. Okay. And if we have to talk about skew symmetric, then just we have to apply one minus sign here. So the difference of a matrix A, a given matrix A, and its transpose, and their half is known as a skew symmetric matrix. So just we this is the process for expressing matrices into the form of symmetric and skew symmetric. So now let's move forward. What it says, this says that for any square matrix A, matrices A into AT and AT into A are symmetric matrices. This says that the matrix is the product of A and AT. That means the product of a matrix and its transpose, and the transpose and its matrix. So these both products are just symmetric matrices. Okay. And here this next point says that if A and B be a symmetric matrices, then AB is a symmetric matrix if AB will be BA. So this says that if A and B both are separately symmetric, and then AB is also symmetric, their product AB is also symmetric, then this property uh, says that this product AB will be equals to BA. So mind this. Now, coming on the next property, this says that all positive integral powers of a symmetric matrix are symmetric. So, actually, let suppose that A is a symmetric matrix. So, all the positive integral powers of this given symmetric matrix A will be just a symmetric matrix, because we have just known a property that if we raise the power of A to the n, and then we have to find its transpose, then this will be equals to the A transpose and its power raised by n. So this is a property, you have to remember this property and just this. Okay, and now let's another property, all positive odd integer powers of a skew symmetric matrix are skew symmetric. And if A is a skew symmetric, then all positive odd integral powers of this skew symmetric matrix will be skew symmetric. So just these are some points and properties you have to just remember and apply them in your uh, questions. Now coming to next point here, the positive even integral powers of a skew symmetric matrix are symmetric. And so the positive even integral power of a skew symmetric, like as if A is a skew symmetric matrix, then all the positive even integral powers of this A will be just symmetric matrix. because of this result. Now we have to talk about the determinant of a square matrix. So what about the determinant of a square matrix? What is determinant? So actually you have just studied about the determinant. You are familiar with this term from your 12th class, but here I will just give a short description to you about this term. Okay. So actually in previous videos I have just discussed about the square matrices. So actually the square matrices, let's recall its properties. A square matrix have its number of rows and number of columns equal, because a square matrix there are the number of rows and number of columns are equal in a square matrices. And so number of rows and number of columns are equal, so there is a leading diagonal or a principal diagonal exist in this square matrix. And so leading diagonal exists, so there are also diagonal elements exist. And so actually this square matrix has also another property. It has also another uh, property, a particular property, that a square matrix has its determinant. So what is a determinant? Actually, how to know this? So just read its definition. What it says: every square matrix can be associated to an expression or a number which is known as its determinant. So just there is an expression, and this is related to every square matrix. Actually, this determinant will not exist if the matrix will be rectangular. That means the number of rows and number of columns are not equal. Then in that case, this determinant will not exist. But if the matrix will be a square, then this determinant will be exist, and there an expression will just related to this square matrix, and this expression or a number or that number is known as its determinant. So how to write this? If A will be Aij be a square matrix of order n, then the determinant of A is denoted by date A or mod A. So this is mod A. You are just familiar with modulus function, so this is the modulus function, and we can call it mod A. So we can denote the determinant of A by writing date A or mod A. So just now coming on next point, this says that only a square matrices have the determinants. So only a square matrices will be possess their determinants. Otherwise, if the matrices are not square, they are rectangular, then there will not any determinants exist. The determinant can be expanded along any row or column. The determinant of a matrix, of a square matrix, this can be expanded along any row or any column of that given matrix. If any row or column of a determinant have only zeros, then the value of the determinant is zero. Actually, these are some properties of determinants. So what about these properties? This says that if any of the row or any of the column of a given determinant have only zeros, there are only zeros in that particular row or that particular column, then the value of this whole determinant will be equals to 0. So this is a very important property, and so you have to just remember this. Now coming on next point, this says that the determinant of an identity or unit matrix is 1. So actually we have just we have just familiar with the identity or unit matrix in previous videos. So actually the identity or unit matrix have just uh, their diagonal elements equal to unity or 1. Okay, so in that case when we find the determinant of an identity or unit matrix, then this is just equal to unity. Okay, so these are some properties of determinants, so let's look upon them. Now here coming on next property, this says that the determinant of a diagonal matrix is the product of its diagonal element. So we have also just got familiar with a diagonal matrix. So what about diagonal matrices? What are they? So actually this is a diagonal matrix is a type of matrix in which there are only the diagonal elements are only non-zero, and any other non-diagonal elements are equal to 0. So in that case, when we have to find the determinant of a diagonal matrix, then we have to just do one thing. We have to just find the product of its diagonal elements. So let's suppose that if A is a diagonal matrix, so that A11, A22, A33, ANN, actually what are they? These are the diagonal elements of this matrix, diagonal matrix A. So in any diagonal matrix say there are only diagonal elements just as non-zeros. So these all are the non-diagonal, sorry, these all are the diagonal elements, and so they are non-zeros. Okay, but actually we are just excluding the zeros part, the other non-diagonal elements. But we should write this diagonal element, matrix in just this way, and these are the diagonal elements of this diagonal matrix. Okay, so if we have to find the determinant of this diagonal matrix, then we have to just do one thing. We have to just write mod A will be equals to then the product of these all diagonal elements. So a11 into a22 into a33, and this goes to ANN. Okay, so this is the formula for finding the determinant of a diagonal matrix if their diagonal elements are these. Now coming to next point. This says that the determinant of a skew symmetric matrix of odd order is 0. What this property says? This says that if there is a skew symmetric matrix and its odd order is 0, that means, sorry, there is just a skew symmetric matrix, and let's consider that its order is an odd number. That means not a multiple of 2. It will be 1, it will be 3, it will be 5, 7, 9, anything, any other odd number. Okay, so in this case, when we should find the determinant of this type of matrix, then this will be equals to 0. So this is a law, this is a property, so you have to just remember this. Now if the even if this skew symmetric matrix will be of even order, that means their order will be 2, 4, uh, anything like this, 2, 4, 6, 8, then its determinant will be a perfect square. Perfect square means like as such a type of number which can give its perfect square, like as 25 is a perfect square because its square root is 5. Similarly, we can also write 100. 100 is also a perfect square. We can find its square root as 10. So these numbers are known as perfect square, and we can easily find out the square root of these perfect squares. And so in this case, if the skew symmetric matrix is of even order, then we can say that its determinant will be just a perfect square. Okay. Now this next property says that the determinant of a triangular matrix is equal to the product of its diagonal element. Okay. So what this says, what about this triangular matrix? So actually we have just uh, discussed about the diagonal matrix. Okay, so similar to a diagonal matrix, there are also such two types of matrices, and these two types of matrices uh, are in one category name as known as triangular matrix. So in this triangular matrix there are two popular types, two particular types. One is upper triangular matrix and second is lower triangular matrix. Okay, so in upper triangular matrix, all the elements actually in the first episode of this linear algebra we have just discussed about the upper triangular and lower triangular matrix, but for a recall we will just give a brief description here about them. So in upper triangular matrix, all the elements below the leading diagonal will be 0, and in the lower triangular all the elements above leading diagonal will be 0. So in this case we can just we have to just find out the determinant of this triangular matrix, and this will be just equal to the product of its diagonal elements. So we have to just find the product of diagonal elements, and this will be equals to its determinant. Okay, and now this is the next point. This says that if A is a square matrix and this n belongs to capital N, that means uh, this n is actually the power raised with this matrix A, and this n is the natural number. So this n belongs to natural number, and then we have to just find this. So what this says that the determinant of the nth power of A, that means we have to find the determinant of a matrix A and its power is n, and so this will be equals to what? This will be equals to the nth power of determinant of A. So these are some properties you have to just remember about them. Now coming on this next point, this is a minor. So what about this minor? So minor is just a term. We have to just find minors of determinants. So what about minors? Let A will be Aij be a square matrix, then the minors of A will be denoted as Mij. Okay, so this A is equal to Aij is a square matrix. Okay, and its minor will be denoted as Mij. Aij will be the square matrix and Mij will be its minor. So what about this Mij? What it says? So M denotes for minor, M represents for minor, and I represents for ith row, and J represents for jth column. So what about this Mij? This Mij says that minor of the element that is in ith row and jth column. So Mij will be minor of the element that is in ith row and jth column. So this is the Mij. And so let's suppose that A will be a square matrix of order 3. So this is a square matrix, and now we have to find its minor. So how to find the minor? So just come here. So this is the actually the process how to find the minor. Minors of a square matrix are submatrices obtained by eliminating the ith row and jth column of that given matrix. So suppose that we have to just find the minors of any element Aij. Okay, so we have to just find the minor of Aij. So what we have to do? We have to just do one thing. We have to eliminate the ith row and jth column of that given matrix. So just come here. What it says, this says that this is a square matrix of a11, and now we have to find the minor of this element a11. We have to find the minor of this element. So let have a look on this I and j part. So this one is the I and j is also, sorry, I is 1 and j is 1 here. Okay, because aij, I is the ith row and j is the jth column, and so in this case I will be 1 and j will be 1. So when we have to find the minor of this element, we have to just eliminate the I rows and jth column. So I means 1, the first row and the first column. So that is the given in this I and j part. So we have to just eliminate the first row and the first column. So after eliminating this first column and first row, we have just only 4 elements, and a square matrix combining these 4 elements will be known as the minor of this element. And when we have to just find out what this minor of this element, then what we have to do? We have to just find out 1, that means first row. So this is the first row, we have to eliminate this, and 2, j will be 2, that means the second column. So this is the second column, this is the second column. So we have to just eliminate this row and this column. So now what we left? We left this. So these are all are the 4 elements, and we have to just make a square matrix of order 2, and this 4 will be the elements of that square matrix. When we have to just find out the minor of this element, then what to do? We have to just eliminate the first row, because 1, I is equal to 1 and j is equal to 3. So third column and first row will be eliminated, and then we got just these 4 elements, and these 4 elements will be the minor of this element. So actually this is the process for finding out the minors of any given element of a square matrix A. So this is M11 will be this. Now what about the cofactors? So cofactors of matrix A will be Aij are denoted as Cij. So let's suppose that there is a square matrix that is A is equal to Aij. Okay, so as we have discussed that minor will be denoted as Mij, the cofactor will be denoted as Cij. So Cij means that uh, cofactor of element of ith row and jth column. Okay, so now cofactors of A is defined as this: -1 into I plus j times of minor corresponding to the element of ith row and jth column of matrix A. So actually that is mathematically we can just write here this thing that Cij will be minus 1 to the power raised by I plus j into multiplied by mij. So when we have to find the cofactor of any given element of a square matrix, then we have to just find the minor of that element. Suppose that we have to find the cofactor of a11 or a12. Okay, so a12 is the element and we have to just find out the cofactor of this a12 element. So what we have to do, we have to just find out the minor of a12, and then when we find out the minor of a12, then we have to just write minus 1 in front of this minor, minus 1, and we have to write their powers as in the terms of I plus j. So this I will be what? This I will be this I, and this j will be this j. So I will be 1 and j will be 2 in the case of a21 element, because a21 lies in the first row and second column. So this I will denote the what? The row, and j will denote the column. So we have to just give here the values of rows and columns, and so we have to just calculate this term. So I plus j will give us sum, and then this will we have to just find this what this exponent, and after this we will just give one thing, and that will be either plus 1 or either minus 1, and so this will be multiplied with this. So let's come on here. So Cij will be equals to two part, mij and minus mij. Okay, so this will give 2 plus 1 minus 1, two values plus 1 minus 1, and so with plus 1 value this will be mij, and with minus 1 value this will be minus mij. Okay, and so if I plus j, if this property is what? If this property is even, then its power will be 1. Hmm? Sorry, its value will be 1, because when this will be even, then the even power of this minus 1 will be what? 1. And so in this case, if I plus j is even, then we will just get here positive mij, positive minor, and if I plus j will be odd, then we will just get here a minus sign. So these are the some things that you have to just keep in mind for finding the cofactor of these matrices. So first of all, we you have to just find out the minors of that given element, and then you have to just find out this term, and then you can find out the cofactors of a given matrix. Actually this cofactor is also a matrix. Okay, so minor is also a matrix. Yeah, we know in this case minor is a square matrix. Yeah, it is a square matrix of or a determinant of order 2. So cofactors are also a matrix. Hmm? Cofactors are also a matrix, and we have to just find out the cofactors of each and every element of a given square matrix, and so this will form a matrix. Okay, now here are some properties. This says that I plus j will be even for leading diagonal elements and odd for non-diagonal elements. So actually I plus j, this will depend what will be the its sum. Its sum will depend on the elements. If that element lies in diagonal element, then this will be even, and if this will lie in non-diagonal elements, then this will be odd. So you can just check the situations and the anything other else that will depend on, and so you have to just find out these cofactors.